All right. Coolio. Recording in progress. Welcome back to lecture 3 of statistical learning for big data. So here we have picking up where we left off with confounding variables. Confounding variable is known as otherwise known as a confounding factor, or a lurking variable is a third variable that is associated with both the explanatory variable and the response variable. So the input versus the output, the independent variable versus the dependent variable. A confounding variable can often offer a plausible explanation for an association between two variables of interest. When faced with a strong association or correlation, such as between vehicles and life expectancy, it can be attempted to immediately jump to conclusions of causality when all we have is a corollary indication. However, it is important to stop and think about whether there are confounding variables which could be explaining the association instead. Okay. A common thing back in the day was childbed fever. This was a great corollary example where doctors often killed mothers giving birth. There was like a 70% mortality rate in hospitals, whereas midwives and home births often only had maybe a 20 to 30% mortality rate. Doctors were astonished. They were like, they take great pride in their medicine and their practices, as they should. Spend a lot of time honing their knowledge, their skills. So people looked into this and determined, that childbed fever was the cause. Something about doctors was causing people to develop childbed fever. It was inflammation, which then led to a fever and would ultimately end up killing the patient. Now, they determined that, okay, childbed fever was the cause. Now, and that was leading to high mortality rates. They also determined that the inflammation was the first symptom, and then a fever developed days later, which ultimately killed the patient. There was no exploration into the confounding variable determining what was causing the inflammation. They just thought that if we can treat the inflammation, we can stop the fever because the fever is the bad thing. It wasn't until somebody asked why. Why are they becoming inflamed? They explored the confounding variables because all they had initially was a correlation. All we knew is that doctors caused inflammation and it killed their patients. But why is this happening? This question of why ultimately led to the modern day formation of the germ theory, and which is what, allowed Louis Pasteur to do his work and refine said theory and pasteurize milk. It was determined that doctors, because they spent so much time learning human anatomy and recording these things, they often did autopsies. There was no concept of germs, microbes, and pathogens being spread between people. So there was no hygiene practices. Doctors wouldn't wash their hands in between an autopsy and going and giving birth, which is disgusting. And more often, and that's why we saw high rates of mortality amongst health professionals versus midwives, because midwives didn't do autopsies. So it led to a position where there was more explanation and exploration needed. We didn't know why autopsies were causing deaths, but all we know was that that was the difference. We have to dive into something. There was some invisible factor here that was causing an issue. We found the correlation. Now we need to find the causation. And ultimately, it was deemed that there are small organisms that can be transmitted um, via different uh, routes of transmission, whether that's in an aerated way. I don't know if that's the right word, aerated. Probably not. Um, but whether that's through animal vectors, human touch and contact, or if it's droplets, things of that, if it can be airborne, I guess is more appropriate. But correlation does not equal causation. always explore all the factors, and some factors may not be readily apparent. I don't think it's as difficult today as it would have been because of our strong scientific foundation, but always think that there could be something more. Correlation is never enough to determine causation. Observational studies versus experiments. How can we establish statistically when an association represents a causal relationship? The key is how the data is collected. We merely collect data after the fact, right? An observational study is with no effort or ability to manipulate variables of interest. There's no independent variable. We simply observe outcomes. The alternative is to intentionally control one or more variables, um, one of the explanatory variables when producing the data to see how the response variable or the dependent variable changes. This is called, this data collection is called a statistical experiment, right? It's just experimentation, right? How can we, in observational study, we observe just natural outcomes, but then through an experiment, we attempt to assign causality. We attempt to understand, let's see, I don't know, what's a good example of that? Crime rates in ice cream. We observe ice cream sales and we observe crime going higher. Correlation. Then in an experiment, we close down an ice cream shop for a day and see if crime drops with it, because that's a explanatory or correlated variable. We would stop ice cream sales to see if it affected the crime rate. And when it didn't, it would determine that these two events are merely correlated, not indicative of, well, they would be indicative of one another. They wouldn't be, I gotta stop saying, they're merely correlated. They're not causally linked. So then we could assign that and move on to other explanatory variables or explore routes that weren't previously explored. What's another reason that people may be committing crime? Poverty in an area, lack of hobbies, too much free time, and this was often the case. That what was a significant event that happened during summer? Temperature rose. Guess what? School got let out too. So we had young men, juveniles with no supervision because their parents still have to work, but now there's no institution to watch them during the day. They roam the streets freely, and idle hands are the devil's playthings. Ultimately, led to the statistically significant rise in crime. By determining that one variable isn't causally linked, it gives us opportunity to explore the real cause of an issue. Another great one, I'm gonna get a little political. Why do you think immigration was so low during the Trump administration? There's a correlation there. Trump's president, lower immigration. Is it necessarily causally linked? No. It's because the world was shut down during a pandemic. All right. Borders were locked down tight. We enacted Title 42, which allowed for complete denial of asylum seekers, refugees, and immigrants to the country on the basis of public health. Borders were closed everywhere. They couldn't make it to the US border. They couldn't travel through various countries to even get here. Borders were shut down. Flights were delayed. Flights were shut down. The world was in lockdown. I'm not going to go any further than that. But the point being, correlation, causation. Okay. Think about it. There's always a why. Think of a why. And literally just keep asking until you get down to bare roots and you get down to fundamentals. What is that why? I'll step away real quick. I'm cooking. Okay, I'm back. Anyway, a well-designed experiment, we can make conclusions about causation when we see a strong association. The method for assigning values of explanatory variables are not influenced by any confounding variables. An experiment is a study in which a researcher actively controls independent variables. An observational study is merely an observation of natural outcomes. Observational studies versus experiments. Both studies below are designed to examine the effect of fertilizer on the yield of an apple orchard. Indicate whether each method of collecting the data is an experiment or an observational study. Causation, caution, it is difficult to avoid confounding variables in observational studies. For this reason, observational studies can almost never be used to establish causality. Researchers find several different apple orchards and record the amount of fertilizer used and the yield of the orchard. What would this be? Take a second. Oh, I'm gonna look at that. This would be an observational study. This is strictly observing natural outcomes that they already had. B, researchers find several different apple orchards to assign different amounts of fertilizer for each orchard. They record the resulting yield from each. This would be an experiment as researchers are directly controlling. Now, let's say that this yields statistically significant results. This may be a contributing factor, but other things need to be involved. When conducting an experiment, all of the variables that are not the independent, the one that's changing, need to be remain consistent. Okay. So even though there may be statistically different amounts of yield in each of these orchards, what needs to be taken into account is nitrogen level of the soil, the type of compost, if it was in a different geographical location, the amount of sun and rain received during these time periods of the apple orchards and of the study. Things of that nature need to remain consistent for the experiment to for the experimental results to be valid or be considered valid. So maybe that would you measure 7 apple orchards all in the same state. So they receive fairly similar weather and have similar soil composition. You measure the nitrogen level of the existing soil before fertilizer is added. Of course, the fertilizer has to be the exact same brand of fertilizer. You can't use richer fertilizer in some orchards versus another. There are a lot of variables that have to be controlled and need to be considered. This even though it intuitively it makes sense, the amount used, of course, may affect the yield, there are other factors at play that need to be considered until you can determine how much a particular variable contributes towards a particular outcome. While it may contribute, it may not contribute as heavily as the amount of water received, or the amount of rain, or the amount of sun that an apple orchard receives over a certain time span. Fertilizer may only play a very small role in it, but still make a statistically significant difference. Okay. That being said, experiments are very difficult. It is what it is. We do our best, we get corollary data, and we judge the world off of it. This is just key to science, and science is hard. Randomized experiments. How can researchers possibly avoid all potential confounding variables? We do a randomized experiment. In a randomized experiment, the value of the explanatory variable for each unit is determined randomly before the response variable is measured. If a randomized experiment yields an association between two variables, we can establish a causal relationship from the explanatory variable to the response variable. So there's some different types of variables in big data, and this affects how we describe them. We have categorical variables, quantitative variables, the shape and center versus measures of spread. We have outliers, box plots, categorical and quantitative relationships, two quantitative variables such as scatter plots and their correlation, and then linear regression between two quantitative variables. These are all various ways that we can look at these factors, these attributes of data, these variables, these start beeping. We learned that there are two types of variables, categorical and quantitative. This description takes two parts: how to visualize data using graphs and how to summarize key aspects of the data using numerical quantities such as called summary statistics. Is there true love for one for each person? Let's take a second to read this. Do you agree, disagree? And Pew Foundation also wanted for it. The survey. One categorical data. Agree or disagree. This isn't quantitative, but then the frequency would be considered. The response is a categorical. The frequency is the what's that called? Quantitative. A proportion in some category can be found by, yeah, this is just telling you how to determine percentages and parts and things of that nature. Visualizing the categorical data. When you have ratios, percentages, it's helpful to visualize in a bar graph, in a pie chart, because they make up certain percentage of the whole. Then it's also helpful to visualize the data in a bar chart or histogram at times, as you can see the frequency, the raw just frequency. Most of the time, it's helpful to visualize in terms of a percentage, as that can be directly applied and is like per capita statistics are often more easily applied to a population than just raw numbers. So that's the advantage of pie charts and proportionality versus just raw counts, you know. Notation for proportion. The proportion for a sample denoted by p hat. The proportion for a population for a population is denoted as p. Two categorical variables, two-way tables. A two-way table is used to show the relationship between two categorical variables. All right. The categories for one variable are listed down the side rows, and the categories for the second are listed across the top columns. Each cell of the table contains the count or the frequency of data cases that are in both the row and column categories. Add a second dimension to a frequency table to account for the second categorical variable. So here we have two categorical variables, your response of agree or disagree, and then the gender associated with it. And here we can see 372 males agree and 363 females agree. And out of the total, we can find a total for this row. How many humans, both male and female, agree with this sentiment? Then we can do it on, we can just continue this process. 70 are undecided and 1800 are disagree. And we can extrapolate data. How many males feel this? How many females feel this? And just how we decide to continue breaking up this data. Sometimes categorical data isn't as intuitive of how to parse it and analyze it, but it can be done. Visualizing a relationship between two categorical variables. So this would be an example of a histogram versus a bar chart, okay? Side-by-side bars, segmented bar chart. So we get the total count of maybe people, well, this is a different one, but this would be a sum of the total. This one bar would be a sum of the total count that agree. Then you see the female contribution and the male contribution to who agrees. But then we would see 150 people in total agreed. That's just kind of a way that you would visualize this chart. One quantitative variable, the shape of a distribution. A common way to visualize the shape of a moderately sized data set is a dot plot. When creating a dot plot we create a dot plot by using an axis with a scale proportionate for the numbers in the data set and placing a dot over the axis for each case in the data set. Here we go. This will help us visualize frequency, median, mode, and range, baby. Those are the bare bones basics of statistical analysis. And dot plots, while boring, can allow us to visualize this data. When we have one quantitative variable, a common way to visualize is the dot plot. We create a dot plot. Yeah. Oh, come on, buddy. Again, quantitative. Great. Then we have an outlier. An outlier is an observed value that is notably distinct from other values in the data set. That'd be this guy over here. It's like, what in the heck? That is just so left field. Like, what's going on? Usually an outlier is much larger or smaller than the rest of the data values. Or you can even have it an instance where the outlier is in the middle. It's the average between the two. Um, the example that pops into my mind would be as something that is easily talked about, I guess, would be intersex people, where most people exist at one of the two extremes when it comes to sexes. Your sexes are one of the two, right? Not necessarily your gender, but your sex. Your sex is typically one of the two. You have people that are born and 90% of the population exists at one of the two extremes. And then in the middle can be the outlier, which is somewhat usually it doesn't always have to be smaller or larger than the data set. It can be in the middle. Um, Maybe not the best example, but just one that pops in my head. And then you have histograms, is a great way. It's similar if you notice. A histogram is a dot plot. It's just bars. All right. It just makes it a little bit cuter. All right. Symmetric and skewed distribution. A distribution is considered symmetric if we can fold the plot, either the histogram or the dot plot, over a vertical center line and the two sides match closely. This would be considered a symmetrical, uh, a symmetrical distribution, not asymmetrical. A symmetrical distribution. Okay. Separate the two. um, Whereas this wouldn't be, and this also would not be, depending on where you drew your line. This could not be folded over one another. So using a curve to represent the shape of a histogram, notice how you can draw a general trend line over the top of a histogram. The histogram, if you know anything about calculus, this gives you the area under the curve. All right. It's like Ramon's theorem or Ramon's? I think it's Ramon's theorem, where we infinitely calculate the area of a rectangle under the graph, and that's a form of taking the integral of a function, because the integral is just the area under the curve. We could uh accurately predict the area under a curve of an interval using calculus. Math is so cool to me. Anyway, symmetric. If the two sides approximately match, then it's symmetrical. This is symmetrical. This is symmetrical. These would be asymmetrical or skewed. Okay. Oh, it tells you symmetrical but not bell-shaped. This would be a Gaussian or normal distribution. All right. If the two sides are perfectly matched, they can be skewed to the right, skewed to the left, and or bell-shaped. The center of a distribution is known as the mean, the average. This is the center. Like I said, you can have an outlier in the center. It's merely the average of the data values, right? The and the average is not always a valuable statistic, depending on how the data organizes itself. As I mentioned, the average between male and female would be intersex, but we don't see intersex making up a large portion of the population. Not that the average isn't valuable to some degree, but wouldn't be in maybe prediction of the gender, not but the sex of a future child, because it occurs at such a low frequency. But the average meets, but it'd be more statistically significant to represent that as the mode. The frequency at which two variables occur may be more indicative of the true performance of the data set or of reality. Two summary statistics that describe the center location of a distribution is often the mean and median. Okay. Mean, as we know, is the summation divided by the number of instances. And then the median of the data set allows us to find the middle point. All right. The median set is a single quantitative variable denoted as M, is the middle entry of an ordered list of data values and contains an odd number of entries, right? If I have the numbers 1, 3, and 5, 3 would be the middle of the data set, or it would be the median. If I had 4, an even number, there's no middle. So what do? We take the two adjacent numbers that would be in the middle. So let's say we have 1, 3, 5, and 7. There's no middle. So what we do is we add the 3 and the 5. We take the average of the two adjacent numbers to the middle, and then we create a median based off those two adjacent numbers. So therefore, 3 plus 5 are the two adjacent numbers to the middle. We create a fifth term, slap that boy in the middle, take the average of the two numbers. 3 plus 5 is 8 divided by the two numbers that we added, the two summations, and then we get 4. 4 would therefore be the median of the data set. And it often splits the data set in half. If there are an even number of values in the data set, then there is no unique middle, and we use the average of the values. I'm gonna go check my food again. That's some jambalaya. All right, since the median cuts the histogram in half, if a histogram is symmetric, then the median is right in the middle and approximately equal to the mean. If the data set is skewed right, then the values in the extended right tail pull up the mean, but have a little effect on the median. In this case, the mean is bigger than the median. Similarly, if the data is skewed left, the mean is less than the median, indicated by these graphs. Measures of a spread. We are interested in not just the center of the data, but how spread out the data are, the frequency over a certain area. This is referred to as the standard deviation. All right. While the centers may be similar, the distributions are very different. The standard deviation statistically measures how much variability there is in the data. This is the equation for standard deviation. You'll notice that this is very similar. We see the same thing occur constantly in statistics. When we compute, what are we computing here? Standard deviation is an error function. Standard deviation is how much do we differ from in this case, the average, but how much do we differ from the expected output, right? In machine learning, we have the generated output versus the ground truth, the label, the expected real world value. Okay. Here, instead of having a label and the expected real world output, the the ground truth here is X bar. That symbol is mean. That's the average. Notice how we measure the difference between the actual value X minus the difference from the average. I mean, it should be like things are clicking now. Things are falling into place. We're seeing why math is built the way it is. I think this is so fucking cool. I part of my favorite part about stuff is like I love the math behind things. I love the theory. I love it to see. This is this is an error function. This is how much does the actual output differ from the average? How much does the actual output observed at a particular point differ from the expected value? In this case, is the average. And we calculate the standard deviation. Gives a rough estimate of the typical distance of a data value from the mean. the larger the standard deviation, the more variability there is in the data and the more spread out the data is. A great instance of this is you typically see standard deviation applied under these Gaussian or normal distributions, where I think in a Gaussian distribution, you have 68% of the data falls within one standard deviation from the mean. So a standard deviation may be here. That would be one asymptote, and then the other would be here. And 68% of the data, oh, I can draw. Forgive me. I'm being a nonsk or whatever. 68% of the data will fall in this. That's within one standard deviation. I forget the symbol for standard deviation. I think it's like I think it's something like this. I think. I can't remember. Will fall in within one standard deviation, whatever that deviation is. It could be, let's say this is the average age of retirement. Most people fall within this. Very few people retire very early. This is another standard deviation, but this is two standard. This would be two deviations. Two deviations. You know what? Deviation it might just be a D. I don't know what the fuck I drew right here. It might just be a D. Anyway, this is the second standard deviation in these boxes, and this will hold 90 or 85. 85% of the data can be represented within two standard deviations. And then as we go up to 3, 4, and 5 standard deviations, it represents a smaller and smaller portion of the population that retires at 5 years old because they inherited a bunch. But the average of the average person retires around 65 or whatever. Yeah, yeah. Fun, cute stuff. Let me trash my garbage drawings and move on. Then we have z-scores. Another way to determine how unusual a single data value is independent of the units used, is to count how many standard deviations it is away from the mean. Yeah. I'm assuming the S here is the count of the standard deviations. I'm actually not sure. I don't think I've ever used z-score, which I should start doing because I forgot this existed. Then you have the 5-number summary. You have the minimum, the maximum, quartile 1, the median, which is quartile 2, and then Q3. This gives us the box plot, which is super valuable in determining where outliers exist. It divides the data set into fourths. About 25% of the data should fall into any two consecutive numbers in the 5-number summary. So we have the IQR, the interquartile range, just the broad range of data values, which is just the range, and the maximum, minimum, the greatest and smallest values in the data set, where everything else is encapsulated by it. And then Q3 and Q1 will give us Q2, of course, the interquartile range. Choosing measures of, let's see. Yeah, so here would be an example of a box plot. It falls outside of it falls outside of the non-outlier portion. So this would be considered an outlier. You have your median, which is like your this is where like 75% of your data lies inside the box. And this is just to measure maximum non-outliers. A box plot is a graphical display of the 5-number summary. Okay. So it shows the minimum, the maximum, Q1, median, and Q3. Draw a numerical scale that approximates the data values. Draw a box sketching Q1 to Q3. Divide the box with a draw line, which is the medium, and then draw a line from each quartile to the most extreme data value that is not considered an outlier. Identify each outlier individually by dotting or plotting a symbol of the asterisk. Asterisk. I always say asterisk. I say it like strict. I guess I shouldn't say that. Outliers and box plots. The detection of outliers is done if it's outside of the quartile range. Okay. We find the quartile range by subtracting Q1 and Q3 from each other. And if it exceeds 1.5 times that value. If it's greater than those lines that we find, then it's considered an outlier. I don't actually know why we use 1.5. I might be a little curious regarding that. I don't know. I'm sure that's not just an arbitrary number they use, but yeah. So here's a quick summary. We learn from data, different types of machine learning can be used in different problems. Learning is not equal to memorizing. We seek not to be right in training, but to accurately model. Collection of data is essential. How are we observing? Are we experimenting? Often you want to use observations in machine learning and not necessarily experiments. Experiments are to determine causation. Machine learning is used for corollary modeling. Okay. We predict trends based off corollary data. Machine learning does not determine causation. We learn different ways to define data based off of their categorical and quantitative values. We learn different ways to describe data via a myriad of statistical methods, the mean, median, mode, range, maximum, minimum, quartiles, interquartile ranges, standard deviations, and things of that nature. We learn different graphical displays such as the bar chart, the pie chart, and things of that nature. And thank you very much. It's jambalaya time, my boys.